In this worked example, we've got a more complex problem. So we've got a manometer with three liquids. So we have water here, then we have mercury, and then we have oil on top of this mercury, and finally we get to water and to our pipe over here. And what the question is asking us to do is it's asking to find the gauge pressure at A. Okay, so as you can see, this is a bit more complex, but once we break it down, it'll be simple enough. And the way that we do that is with the chain rule that I talked about in the lecture. So just to remind you, the chain rule is you take if you want to work out the pressure at your final point, then what it is pressure at your initial point plus all the sum of your down hydrostatic pressures minus the sum of your up hydrostatic pressures. So what does that mean? So we're going to start over here, okay, and we're going to go down this side. So we need to sum up these pressures, go round the bend, we sum this up once, and then round here, and then we're going to go down again. Okay, so we've got a number of things to consider here. Now just notice on the bends, so if you consider the mercury here, we don't need to consider this because the pressure here will be the same as the pressure here. Okay, so we don't need to do that bit. And likewise with the oil, we don't need to consider anything in the actual U bend because the pressure here will be the same as pressure here. So it's just the bits in the middle that we need to do. Okay, so if we start off, so I've just got the solution written out here. So the pressure at A, which is what we're trying to find, is equal to the initial pressure, which is atmospheric pressure here, it's open-ended. Then as we start to go down, our first term, we've got a 90 centimetre head of water, okay, so that's this term, so 0.9 times G times the density, but it's the density of water, okay, times by 1,000. Then we have this head of mercury, which is 60 centimetres, okay, so it's 0.6 times G times the density, but just be careful to make sure you get the right density. So it's density of mercury here, which is 13,600. Then we come around this bit. Now here we have an up term, okay, so we're going from this level up to this level, which if you add that 30 centimetres onto this 150, so that's 180 centimetres. And this is oil, okay, so we need to use the density of oil, so our up term is 800 times gravity times 1.8. And then finally, once we've come around this last bend, we then have a down hydrostatic pressure, 150 centimetres of the water, so 1.5 metres, times gravity times density of water in this instance. Okay, so we can plug those into our calculator, and then what we work out is we work out the this is the up, the down minus the up, and that's equal to the difference between our the pressure in our pipe A and the atmospheric pressure. So that's the absolute pressure there, because we've included atmospheric pressure, but if you remember, pressure absolute is equal to the gauge pressure plus the atmospheric pressure, and we already had the atmospheric pressure in our previous terms, so they cancel out. So therefore, the gauge pressure at A is the sum of the two numbers, which gives you around 90 kilonewtons per meter squared, or 90,000 pascals.